Okay, everyone. Has everyone picked up their clicker? Everyone got their clicker? Okay, we're going to take a quick attendance, so go ahead and press number 1. Or number 2. Doesn't matter, as long as you... Everyone good? Anybody not get a clicker from last time? Is new to the class? We're all good? Get your clicker. So if you come in a little late or something, just make sure you get with me so you're not counted absent. I wouldn't want you to be here and count. I think I counted, let's see, last time I went purely off of this. So I have Brinkman, Forsman, and Perez counted absent. So if you were here, just talk to me after class, okay? Let me see here. Man, how do we have so many people in this class? Maybe, what about back in that corner? Is there someone on that corner? Yes? How about at the end of that desk? Or right there. There you go. Go ahead and click number 1, Tamikis, on your thing. Where's Tim? Did he leave? No. Tim walked in. Did he leave? He walked in. Can you click 1 for him? Thank you. All right. All right, let's talk about possible homework questions. Questions over homework? No questions. Really? Okay, number 28, number 24, 3-5. Okay, 24 and 28. Let me start with 24. So number 24, you're asked to find the derivative of the function y equals cosine inverse or arc cosine of arc sine of t. All right, so what we have here is functional composition, right? We have a function sitting inside of another function. So if we're going to take the derivative, we're going to need to apply which rule? Chain rule, right? Chain rule always starts by taking the derivative of the outside function, evaluating that, and then taking the derivative of the inside one, multiplying together, correct? All right, so the derivative here will be whatever the derivative of cosine inverse of something is. So I'll just remind you over here. If we have cosine inverse, let's say, of u, the derivative of that, now I don't believe we derived that formula in class, but the formula was in that section, correct? So what is the derivative of arc cosine? Also, it's on your cheat sheets, right? Okay, so what is the derivative of arc cosine? Square root of 1 minus x squared, but in this case, I'm using the variable u, right? So it'll be negative 1 over the square root of 1 minus u squared. And then you'll have to say times the derivative of u to finish off chain rule. So times the derivative of whatever the u is. So for us in the problem, u is what? Arc sine of t. So this is going to become negative 1 over the square root of 1 minus, then the arc sine, I'm going to put in parentheses, arc sine of t, but that quantity squared, All right, so that's your derivative of your outer function, cosine inverse. Now I need the u prime over here, which is the derivative of what's in this. So what's the derivative of arc sine of t? 1 over the square root of 1 minus the t squared. Bless you. Right? And then you could say times the derivative of what's inside this arc sine, which is derivative of t, which is going to be 1 because we're assuming that t is the independent variable. So we're done here. I mean, you could try cleaning this up. The only thing you could really do is maybe squeeze this together with this underneath one big root, but we'll just leave it like that. Okay, is that all right? All right, for number 28, you've got arctangent of square root. So y is equal to, instead of writing arctangent, I'm going to put tan with our little -1, and then the square root of 1 minus x over 1 plus x. So again, we have composition. We have the arctangent function. Inside of the arctangent function, we have what? Quotient, but what's before the quotient? If we're working our outside in. This is going to be chain rule. So the outer function here would be arctangent. The next one inside would be the square root, and then inside that would be your quotient rule. So you could look at this as a composition of 3 separate functions. So let's start out with what the derivative of arctangent of something is. Again, that's something I did not show in class, but it's one of the formulas. So what's the derivative of arctangent of something, of u in this case? 1 over 1 plus u squared, right? Would it be okay to write that as 1 over u squared plus 1? Yes, right? Because addition is commutative. So just be aware, anytime we see the sum of 2 perfect squares like that in the denominator, with 1 on top, that is the derivative of arctangent. All right, so then we would have times u prime. Forgot to put that out here. Times u prime, times u prime. So in our problem, the u is everything we see here, right? That's our u, everything we see. So you're going to need to be able to take the derivative of that. Would you like to do that on the side here, maybe? Take the derivative of all this? Okay. So if I have, maybe we can rewrite it. Why don't we write it 1 minus x over 1 plus x to the 1/2 power. That's the same as the square root. And what I want is the derivative of this, right? So that's a little miniature chain rule here, right? Start with the power. Power comes out. We subtract 1 from the power, don't we? So this will be 1/2 comes out. It's everything here to the -1/2. And the everything that we were talking about was 1 minus x over 1 plus x. Do y'all agree that that's the derivative of this so far? Now times what? The derivative of the inside, which is your quotient rule. So however you learn the quotient rule, the way I teach my class is it's the derivative of the top times the bottom minus the derivative of the bottom times the top, all of that divided by the bottom squared. F prime g minus g prime f over g squared. There's different ways you hopefully learned it, but you know, it's got to be somewhere in there, either on a piece of paper that you refer to or up here somewhere. Hopefully it's up here. All right, so what is the derivative of the top? -1 times the bottom, which is 1 plus x, minus, because it's quotient rule, derivative of the bottom, which is 1 times the top, 1 minus x. I'm running out of room, sorry. All over bottom squared. What does the numerator simplify to be here? negative 2. All right, so if you distribute through here, some x's cancel. So we're looking at this. We've got 1/2. How do I want to do this? Let's see if you are okay with this. 1 plus x to the 1/2 over 1 minus x to the 1/2 times negative 2 over 1 plus x squared. So what did I do here? What does raising a fraction to a negative power allow you to do? Lets you flip it, right? You can flip the fraction over and make it a positive power. And then so when I flip this fraction over, it's all of it to the positive 1/2, and then I apply the positive 1/2 to both the numerator and denominator. Now, why would I do that? You see these two have the same base, which means that I will be able to somehow put these two together. I kind of saw that while I was doing the problem. So if we have the 1 plus x raised to the positive 1/2 over 1 plus x raised to the positive 2, the property of exponent says, like, what? X to the n over x to the m is equal to x to the n minus m. So what happens if you take 1/2 and subtract 2? You get negative 3/2. So we should wind up with this 1 plus x to the negative 3/2. But I'm not going to leave it on top negative. I'm going to put it back down the bottom, right? Okay. And then what about these 2's? That 2 and that 2 cancel. I'll still have a negative 1 there. All right. I'm going to put all this back up here, right? I've got to get an answer here eventually. This is all scratch work I did on the side. So I'm ready to kind of throw it all together, and then I'll clean it up too. So my derivative should be, first of all, it was 1 plus 1 over u squared, right? So 1 over 1 plus, now what was the u that I'm squaring? It's all this, right? Square it, and I just get negative 1 minus x over 1 plus x. So this is going to be 1 minus x over 1 plus x times, my writing looks all shaky. Plus what? Times what? So what was over here? Negative 1 on top, right? Negative 1 on top, and then what was still on the bottom? Okay, 1 minus x to the positive 1/2, and then we also had 1 plus x to the 3/2. Let's vote real quick. Is everyone good up to this point? It had a square root when it started, remember? It was negative when we did it. So when we actually would have done this part right here, we would have got 1 plus x to the negative 3/2, right? Which would have meant it was on top with a negative power. So I went ahead and dropped it down and made it positive. Okay. That's pretty much the derivative. There's still a lot of work that can be done here algebraically. Now, who asked the question about this one? Was it more the derivative or was it the algebra now? The derivative. So, okay, up to this point then? Okay, so I'm not going to go through the rest because this is part of why you do your homework, to get through the algebra of this. But, you know, what I would do is I would combine these two with the common denominator, and then I would basically simplify this complex fraction. Once it was simplified, then things would cancel here with some of the stuff here, and you would get a nice cleaned up answer. All right, but I won't go through that. Okay. Good question. All right, let's get back to where we were last class then. I had shown this derivative, right? We showed that this arc sine derivative was equal to the 1 over the square root of 1 minus x squared. And then I don't believe we did this, right? Did we do this one? No, we didn't. Okay. Very similar to something out of your homework. So what I think I'll do is I'm going to skip the example 4 and go to example 5. I think that one's a little more constructive. I just updated the notes that I have online for you. I went in and did some adjustments. They actually go all the way up to 6.2 now. So if you want, you can print those out. So let's see here. We have y equals the square root of sorry. No, I'm doing the wrong damn problem. Arc sine of xy squared equals 1 plus xy. And we're asked to find y prime. The problem that we have here is that we have an equation that cannot be solved for y explicitly. There's no way to isolate y on one side of this equation because the y is trapped inside the arc sine. You can't get it out of there unless you apply a sine to this side. But if you apply a sine to this side, you have to apply a sine to that side, which traps this y inside the sine. So no matter what you do, you cannot get this y isolated. So this is what we call, anyone know what this equation is called? An implicit equation. So since it's an implicit equation, we use implicit differentiation. So that means we just take the derivative on both sides of the equation. We make sure we follow all the chain rule, product rule. We treat the derivative of x to be 1. We treat the derivative of y to be y prime or dy dx. All right? So I like to represent that I'm going to take the implicit differentiation with the squiggly line. What is the derivative of arc sine of all this junk right here? 1 over square root of 1 minus all that junk squared, right? So if I square it, I get x squared y to the 4th. So I'm just squaring the x, squaring the y squared. And then I'm done with the arc sine derivative. I need to go inside and take derivative of x times y squared, which is a product rule, right? So I'm going to attach to the end of this times product rule is going to produce what the derivative of f times g is f prime g plus g prime f or something like that. So what is the derivative of my first function? I'll call it f, and then here's g. What's the derivative of the f function here? 1 times g, so this is just going to give us what, y squared? And then plus, now the derivative of y squared, which is 2y, careful, 2y y prime, right? Because you take derivative of the y squared first, it's 2y, then you take derivative of y itself, which is y prime. Then finish off the product rule, you have times the x. Are we done on the left side? We did the derivative of arc sine is here. The derivative of what was inside of it is here. There's nothing left, right? Yes, sir. Y prime is not 1. X prime is 1. Okay? X prime is 1. The reason why is because we are assuming that y is a function of x. So we don't know what y is really. So when we're asking how fast is it changing instantaneously, we can't say that that ratio is 1. With x we can because it's kind of complicated. When we say x is the independent variable, we vary x in a constant rate. So therefore the rate of change of x is always 1. But since y is some function of x, it could be doing other things, its rate of change may not be 1. Okay, we are done on the left? Yes? That's right, dx, dx, for the implicit, the Leibniz notation makes that a little more clear. Dx, dx versus dy, dx. This is dy, dx. When you take derivative of x with respect to x is dx, 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 dx is 1. So equals 1 plus xy, take derivative here. So derivative 1 is 0 plus product rule again, right? What do we get there? We do it all. So depending again on how you learned it, that's what you get. For the x, yes, but I didn't put it. It's right here. 1 times y plus y prime x. There's a 1 right there. Were you doing product on this? Product right here. So that's your raw derivative. You've got your y primes in here. Again, this would just be an exercise in the algebra. You would need to distribute this entire thing through to release the y prime from this parentheses. Then you get all your y prime terms on one side, everything that doesn't have y prime on the other side, factor out a y prime, you're done. Again, I'll leave this to you because this is an exercise in algebra at this point. Okay? We good? Yes or no? Why is my chart not showing up? Everything that does not have a y prime goes on the other side. Yes, but you can't get this y prime out yet. You have to distribute this through. And then you would take this y prime term. I would leave this one here. Bring this one over. Then this nasty one here, take it to the other side. And then factor out your y prime. Then divide through. Some people aren't voting? Okay. Okay, so last example in 3.5. A rocket is fired straight up with the speed of 1,000 miles per hour. So this rocket has a constant speed, going straight up. An observer who is a mile away from the launch point is tracking the rocket with binoculars. At the moment the rocket is 3 miles high, how fast is the observer's angle of inclination changing? What is that in degrees per second? Okay? All right, now, yes. Unless it says degrees per second or something like that, we'll always say radians. Yep. All right, so let's see if we can get a visual. This is a related rate problem from Cal 1, but now what we're going to do is see how possibly we could use this inverse trig stuff to help us. All right. So I'm going to draw a picture real quick. I'll cheat a little bit. I have a rocket. Okay, here's my rocket. It's going up. I have an observer. We will not account for how tall the observer is. We'll just consider the observer to be a point on the ground, right? Are you sitting on the ground? We can't have that. Let's just try. Are we out of chairs? One chair here. Okay. Can we roll him in the end here or something? No problem. There's also, well, you know what? You want to sit on this one? Just slide it that way so you can see around me. You sure? There's room there too. Figure it out. Okay, so we have an observer on the ground, right, which we'll look at as a point. That observer is 1 mile from the launch site. So we're going to say that the distance from here to here, right, is 1 mile. I'm just going to put 1. We'll just all assume that we understand it's 1 mile, all right? And the rocket is traveling at a speed upward of 1,000 miles per hour. That is not the length of the side, right? That is the rate at which that side is changing. So in the problem, there are a couple of things that are varying with time, right, as time goes by. The height of the rocket and the angle from the observer to the rocket. So I'm going to label those sides. I have from the rocket to the observer, and then I have this distance here, which is also changing. I will call this side over here, how about h for the height? Is that okay? It's changing in the problem. I could also label the hypotenuse, but am I interested in the hypotenuse? Do I want to know how long the hypotenuse is here in this problem? No, I want to know the rate at which the angle is changing, right? So I need to label that variable as theta. So let's write down some stuff we're given in the problem. And then what is it that we want to know? So we want to know the what? What is theta, or what is the rate at which theta is changing? That's different, right? Theta is just an actual angle. The rate at which it's changing we call d theta dt, the rate at which theta changes with respect to time. So we want d theta dt, right? That's what we want. When do we want that? There's a specific point in time when we want that. When the rocket's 3 miles high. So when h is 3, right? We want this when h is 3. What's the given information here? We know that the rate of the rocket, right? Which you could also look at as the speed at which h is growing, right? The speed of the rocket is how fast the length of h is changing. So instead of using some just arbitrary variable, I'm going to use the h that I have in my right triangle. Right? I did draw a right triangle here. Good? Okay, quick poll. You okay up to this point? All right, good. So now, what is it that I do? If I have everything, I've written down what I've been given in the problem, I have what I want, what do I have to do now? Find an equation that relates the two together. It may not be a function because it may have more than one variable in it, so I'm going to say equation. You have to find an equation that relates the variable h here to the theta. And you can use anything you know. In this case, we have a right triangle, so there's a lot we know about right triangles. Specifically, because we're dealing with an angle, how about a trig function? So what's the trig relationship here? We could use sine, right? Sine is opposite over hypotenuse, but we don't have any information about the hypotenuse, do we? Tangent is opposite over adjacent. We have both the opposite and the adjacent. The adjacent's never changing. So I could write down that equation. According to my picture, tangent theta is equal to h over 1, which is just h. And that is the equation that relates the two variables together. And then you could go about taking its derivative, yes? I'm going to do it the way that we normally did in Cal 1, and then I'm going to show you what this information from 3.5 can help us do, all right? So if we did not have 3.5, we would just continue now by taking the derivative. We would be taking the derivative on both sides of the equation implicitly with respect to time. So what is the derivative of tangent theta? Secant squared theta, then chain rule says times the variable d theta dt. And we're done on the left side. What's derivative of h with respect to time? dh dt. Do you know what d theta dt is? No. Do you know dh dt? Yes. Do you know the angle at the specific moment in time? Not right off the bat, but couldn't you find it? Because you could replace your h with 3, and then you could come in here and find theta. So I'm going to stop here. This is how we would do it in Cal 1, all right? So here's the variation of the same problem using the 3.5. Write down that same equation. But before I actually take the derivative, I'm going to actually try and isolate theta. Because you see here, dH dt, the thing that we wanted, was just sitting here, right? I'm sorry, no, dH dt is what we're given, right? D theta dt is kind of trapped over here with this other stuff. Wouldn't it be nice if our answer just had d theta dt just sitting there on one side by itself? So what I'll do is I'll take the arctangent on both sides here before I take a derivative. So if I take the arctangent, what's arctangent of the tangent theta going to be? That'll just be theta, but you have to do it to the other side, arctangent of h, right? So the left side is theta, the right side's arctangent of h. And now take your derivative with respect to time. D theta dt on the left. On the right, what's the derivative of arctangent of something? 1 over 1 plus, that's something squared, then chain rule, times dH dt. Now, looking at these two, do you see the contrast? Do you see that one of them is a lot easier to evaluate right now than the other? Like on the one on the left, we had to figure out what theta is, right? We had to go recover theta from our triangle. On this one, what's the only thing we need? H, which we know it's 3 at the moment in time, right? And dH dt is 1,000. See how much easier that is to do? Just by doing that simple composition with the trig on both sides real quick. But you had to know what the derivative of arctangent was to be able to do it. Okay, that's it. Not going to finish it out. So that concludes 3.5. We're going to start 3.6. And it's hyperbolic functions. Close this out. And I thought I would motivate this with a with an example for you. I'm going to go here and I'm going to plot a quadratic function for you real fast. I'm going to need a volunteer also. Can everyone see? That's x squared. Can everyone see that okay? See if we can get a volunteer or not. Looks like you're the volunteer. See if we can do this. Just hold that string. Comes this way? Yeah. Okay. This is a parabola, all right? And what we have here is just a string, right? And what we're going to do is you're going to attach your end to that end up there, and I'm going to attach my end to this end up here. And what do you think? Does that parabola match up to this string pretty good? Pretty good? Do you think that there's a way that I could modify the quadratic function to make them lie on top of each other perfectly? Let's take a vote. You don't get to vote. How many of you think that there's a way that I could line these up hold on. With you can modify the quadratic however you want. Do you think that there's a way to get some quadratic out there to match up with this? Yes or no? Okay? All right. So we got a lot, almost 80% saying yes. The answer is no. Okay? There is not a way to get a quadratic. There does not exist a quadratic that would model this hanging rope perfectly. All right? It's impossible. All right, let's put your arm down. You're getting tired. So stay there. Hold on. There is, however, a function that will do it. And it's called a catenary. And it involves an inverse trig function. I have not tried this. I don't know if this is going to work or not. Okay. Maybe you're more convinced, okay? Any wire that is hanging, subject to gravitational forces on Earth is going to have a certain shape to it, right? Now we could make it like this, right? But that would just change the function here. But it's not a quadratic. All hanging wires are not quadratic functions, all right? They are. We're done. Thank you. Okay. They involve these things called hyperbolic trigonometric functions. So any hanging wire can be modeled by what we call a hyperbolic cosine function, but a quadratic's not going to work. So you imagine all the poles out there with the electricity, right? And I mean, there's all these wires, and engineers want to know certain things about those wires. One thing an engineer might want to know is, if you know that your wire has a certain weight to it, right? Then you'd like to know what forces your what is that thing called? Your insulator that holds the wire, electric wire, the insulator, made usually out of like some sort of glass or ceramic. Do y'all know what I'm talking about or not? What sort of forces are those subject to? Well, that would be something like, here's my pole. Okay, we've got our wire. And the force that's acting on this point right here is acting in the same direction as the tangent line at that point. Wouldn't it be? Imagine a tangent line moving along this curve. When you get up to that point, there's a tangent line. And so all the forces acting on that point is equivalent to someone pulling straight along that red line instead of along the curve, if that makes sense. So if you want to know things like that, then you're going to want to know what the derivative is so you can figure out that slope, right? Well, the function that you're taking derivative of needs to be a function that models that wire, and it's not a quadratic. So that's just one example of why it would be important for us to understand these functions. All right, so there are 6 new trig functions that go along with our basic trig functions, right? Sine, cosine, tangent, cosecant, secant, cotangent. Now we have the hyperbolic trig functions. And all of these trig functions are somehow connected to the exponential function. So they are a linear combination of the exponential functions. Linear combination of exponential functions. What does that mean? All you do to create the hyperbolic sine function is you take e to the x and divide it by 2. And then take negative e to the negative x, which is another exponential function, and divide it by 2. Put those two together. When you do that, you get the hyperbolic sine function. The cosine hyperbolic is the same as the sine hyperbolic. You'll hear me say sine hyperbolic and hyperbolic sine. I switch the order of where I put the hyperbolic. It really just depends on you. All right, either way. People understand what you're saying. It's good enough. So this one is almost the same as this one, except this one has a plus, right? The cosine hyperbolic has a plus in between. This one has a minus. Do you all see? I know it's kind of hard to see this, but they're in your notes that I provided you also. And then everything else is just what we normally thought these functions behave like. Tangent hyperbolic is just sine hyperbolic over cosine hyperbolic. Cosecant hyperbolic is just 1 over sine hyperbolic. Secant hyperbolic is 1 over cosine hyperbolic, and so on and so forth, right? Okay. Here are the graphs. Remember what sine looks like, right? Sine is a wave. Okay. Hyperbolic sine doesn't look like a wave, does it? Cosine hyperbolic, right here. There's that catenary, the hanging wire, right? That's a little better. Here's tangent hyperbolic. Cosecant hyperbolic. Let me take some of these out of here. Remember, cosecant hyperbolic is the reciprocal of sine hyperbolic. So wherever sine hyperbolic was 0, we should have an asymptote on the cosecant hyperbolic, right? And then same thing, the secant hyperbolic, check this one out. Take the sign. Secant hyperbolic is the reciprocal of cosine hyperbolic. Cosine hyperbolic does not have a 0, doesn't have an x-intercept, so there should be no asymptotes on its reciprocal. So here it is right here. You can look at it this way. On cosine hyperbolic, as you move out to the right, cosine hyperbolic gets bigger, which means its reciprocal gets smaller, right? And then here's the blue is the tangent hyperbolic, the red is the cotangent hyperbolic. You don't need to know all these graphs, okay? You don't have to have them memorized. I just wanted to show you what their behaviors are like because they don't look anything like our normal sine, cosine functions do. All right, so now we want to show some, you remember with the normal trig functions, we had these identities, right? Pythagorean identities, right? Sine squared theta plus cosine squared theta equals 1, all these different things, right? What I'm going to show you is that there are a bunch of identities here that you can refer to later on, right? Here's a bunch of them. We're going to show this one up here, all right? Before, though, let me just show you, go through these. What is this identity called, or what is this called when sine hyperbolic of negative x is the same as negative sine hyperbolic of x? Even odd. This one is what? Odd. This one? Even. So if you plug in a negative into the sine hyperbolic, it's the same as plugging in a positive and then changing the sign negative. This one says for cosine hyperbolic, it doesn't matter. Plug in a positive or a negative number, it gives you the same value. This is like the Pythagorean identity. We had sine squared theta plus cosine squared theta was 1. For hyperbolic functions, it's cosine hyperbolic squared x minus sine hyperbolic squared x equals 1. And then this one's created off of just using the reciprocal identities. Sum formulas. Do you remember what the sum and difference formulas for sine and cosine? Remember those? Those were pre-cal stuff. So let's establish this identity real quick. I want to show that cosine hyperbolic squared x minus sine hyperbolic squared x is equal to 1. And the only thing I know is the definition of cosine hyperbolic and sine hyperbolic. The definition of cosine hyperbolic is e to the x plus e to the negative x over 2. And then I'm going to subtract from that e to the x minus e to the negative x over 2. So we are given this information, all right? We are given the definition of cosine hyperbolic, right, of x is this. Now I need to do what with this? Square it, and then over here, this is sine hyperbolic x, and I need to square that. So unfortunately, we have to square each of these. I need to show that that's 1. So when you square a fraction, you square the top and bottom. And I think what I'll do is I'll go a little slow on this first one. I'm trying to show that this is going to be equal to 1, right? So when you square the numerator, there's 2 terms. You have to actually FOIL it out. And then I square 2, I get 4. Same thing over here. All right. Let's square out this numerator here. What would you get if you multiplied this out. So e to the x times e to the x is what? E to the 2x. What's e to the x times e to the negative x? 1. Right? Because you add the exponents, don't you? What's x added? X plus negative x? 0. Right? Anything to the 0 is 1. Well, except 0, right? So this is going to give us 1. And then what about here? Do these inner ones. 1 again? Then do the outer ones. What's e to the negative x times e to the negative x? E to the negative 2x. All of that over what? 4. Okay, minus, now let's FOIL out the top here. We get e to the 2x. This time, though, what? On the second multiplication here to here. It's negative 1, right, instead of positive 1. So we get negative 1 here. What about the inner one? Negative 1. Then the last one, negative times negative is positive. So plus e to the negative 2x. All of this over 4. Now you have the same denominator here, right? So you can put these together. And we just need to be careful because this negative sign is going to change all the signs here, right? So check out what happens. This e to the 2x, we are going to subtract e to the 2x, aren't we? So it's going to go away. So these two are going to kill each other off. I'm going to have 1 plus 1, which is 2. And then over here, what? 1 plus 1 again, because the negative distributes. So we're going to have 1 plus 1. So that's going to give us 4, isn't it? And then what about the positive e to the 2x, negative 2x? And then this one is going to be take away that, right, because of the minus. So they kill each other off also. So what you're left with was 4 on top and 4 on bottom, right? 4 over 4 is 1. Right? That's just showing that identity. I wanted you to see how you could manipulate these in their exponential form. Let's vote. Y'all good? Okay? Is that all right? Oh, wait, hold on. I got to start it. There you go. All right. So just be aware of these identities, all right? They're in your book. Now, since we have these new, right, 6 new hyperbolic trig functions, as we might expect, we're going to have 6 derivatives, right? So I'm not going to go through this, all right? I'm not going to show you that these are true. You could do it. Like, how could you show me that the derivative of hyperbolic sine of x is equal to cosine hyperbolic? You would take that e to the x, all that stuff over to, you take its derivative, and what you'd wind up with is the cosine hyperbolic function. So the derivative of sine hyperbolic x is cosine hyperbolic x, just like it was with sine, wasn't it? Now here's a little kink in the armor here, right? This was not what we had remembered, right? The derivative of cosine of x is negative sine x, but with hyperbolics, it's what you wished it was back in Cal 1, right? The derivative of cosine hyperbolic is sine hyperbolic, not negative. Derivative of tangent hyperbolic x is secant squared hyperbolic x, yes. Yes, yep. You could prove all of these by just taking these and rewriting them in their exponential form, the way that they're defined, and then just taking the derivative. It's a good exercise to go through that. Derivative of cosine hyperbolic is this and this and that. All right, there you go. So here's an example. We'll just do this quick derivative. So if we have that y is equal to x secant hyperbolic of e to the x, we're asked to find y prime. So y is solved for in this problem. So we don't need to do implicit differentiation. So the derivative of y is, so what do we have going on the right side here? We have product rule right here. And then on this one, we have a little chain rule. We have a secant hyperbolic function. Inside of that, we have e to the x. So let's just start with the product. Derivative of x is 1. I'll put it times the secant hyperbolic e to the x. And then plus, what is the derivative of secant hyperbolic of e to the x? So according to this, derivative of secant hyperbolic of x is what? Negative secant hyperbolic of x, tangent hyperbolic of x. So it's going to be secant hyperbolic e to the x, tangent hyperbolic e to the x. So that's the derivative of secant hyperbolic of something, right? Then the derivative of second, oh, forgot to put, did I put it on here right? Okay, I did. Forgot my negative. I need to finish off the chain rule, don't I? Derivative of what's in here is e to the x. So that gets tacked on to the end there, right? That e to the x cannot go inside here with these, right? Just attached to the outside multiplication. You could go on with this. You could factor out a secant hyperbolic of e to the x from both of these, but that's pretty good right there. X. Man. That's y prime. This is derivative of e to the x, and then this was finishing off product rule. Okay, now, if we have 6 hyperbolic trig functions, right, we know their derivatives now. But for each of these hyperbolic trig functions, there is an inverse hyperbolic trig function. And here's what they are. The inverse of the hyperbolic sign, or the hyperbolic sign inverse function, is natural log of x plus the square root of x squared plus 1 for all x in the real number system. All right? That's the definition of the inverse of the hyperbolic sign. And here's the definition of the inverse hyperbolic cosine and the inverse hyperbolic tangent. I'm not including the other 3, okay, because they're very seldomly used. So these are the only 3 that we're going to look at. What I'd like to do is show where this one comes from, because it looks pretty nasty, doesn't it? Let's show where that thing is generated. So we want to show that the inverse of the hyperbolic sign of x is equal to the natural log of x plus the square root of x squared plus 1. So how in the world are we going to show this? What's the only information we know? The only thing that we know is the definition of sine hyperbolic, right? We were given that sine hyperbolic of x is equal to what? E to the x minus e to the negative x over 2. That's all we know, right? We need to show that the inverse of that function is that one up there. So do you remember in college algebra how you found the inverse of a function? So this is our function, right? We're saying this is f of x. I want to find the inverse. How did we do it? Replace f of x with y, then switch x and y variables, then solve for y. Sound familiar? Maybe it's been a while. So I'm going to first replace f of x with y, rewrite everything. Now I'm going to switch the x and y variables. That means everywhere I see an x, I put a y. Everywhere I see a y, I put an x. So this becomes x equals e to the what? Y minus e to the negative y over 2. Yeah, solve for y. So how do you solve for y here? What's your first instinct here? Multiply both sides by 2. All right, I like that. So let me change the order a little bit. E to the y minus e to the negative y equals what? 2x. All right, let's take a little vote here. Are we good up to this point? Does anybody have any idea of what to do now to try and get y by itself? Natural log, you're thinking natural log, right? Especially because you know that we're supposed to get a natural log over here, right? But we run into a little bit of an issue because if you do this, don't write this down, if you try and take the natural log right now on both sides, the problem you have is that natural log of this, you cannot break this down. Like if it was just natural log of e to the y, that would become y, wouldn't it? Because they're inverses. But it's because you have the subtraction between them that you can't do that. Further, you don't have a way of breaking it into 2 natural logs. Because the rule for 2 natural logs was this. Natural log of u times v became natural log of u plus natural log of v. That's okay if you have multiplication in there. But if you have addition or subtraction, there is no splitting. All right? So it's good to think natural log, but we're not going anywhere with that. As a triangle, in what sense? Let me get around you real quick. I don't know. I haven't tried that before. I'll go with your suggestion and see if it leads to anything. What's being suggested, and I'm not sure why you're suggesting this. Maybe you can elaborate? No? Is this just an instinct thing you're wanting to do? And then you want like this? Okay. I'm not sure because we don't know anything about this. I mean, the only thing we do know is that this side is the square root of that squared minus that squared. That would be kind of tough. So look, this is Cal 2, right? So it's time to show you some math, some algebra that's a little more complicated than what you see in normal, everyday Cal 1, pre-Cal, college algebra, all right? Believe it or not, we will be able to solve this using the quadratic formula. We have to first see it's a quadratic. All right, let's see what happens here. Let me rewrite this. Well, we may be able to. Let's see what happens. I'm going to multiply both sides of this equation right here by e to the y. Now, just follow me through with this, all right? And consider this, if you have never seen something like this before, consider this the first time you've ever seen this, and now it is in your bag of tricks. And it doesn't come up often, but when it does, it's super powerful if you can pull this one out, all right? So what happens when I multiply e to the y times e to the y? Get e to the 2y, don't I? What happens when I multiply e to the y times negative e to the negative y? I add their exponents, right? We get 0, so it becomes 1, so it's just minus 1. And on the other side, 2x e to the y, right? Now I'm going to move everything to one side of the equation, left side. And notice the order I'm putting things in. And this is just outstanding. I really enjoy this part of math because it's so unnatural to want to do this, but it works. All right, and one more line, and then maybe you'll see what I'm going to do. Notice that, you know, e to the 2y was the same as e to the y squared, right? This right here is e to the y, and over here, you know, we've got a number by itself. So what I'd like to do is make a substitution in the problem. I would like to let u be equal to e to the y, which means I'm going to replace all my e to the y's with u's, but at the end I need to go back and switch. Don't forget we're going to need to go back, right? Okay, so if I rewrite this problem, replacing the e to the y's with u's, what would I get? U squared minus 2xu minus 1 equals 0. Now, I think this is the great thing about this, all right? I hope you are all very comfortable with the idea that if someone gives you ax squared plus bx plus c equals 0, that this is a quadratic equation, and we can always use a quadratic formula on it, right? But what you were always told was that x here was the variable, right? That you're trying to solve for? Yes? And you were always told that the a, the b, and the c were always what? Constants. But they do not have to be constants, as long as they aren't the variable you're trying to solve for. So for us, our variable is u, right? Our constants are actually the number in front of u squared, which is what? 1. That's like the a. The b for us is what, though? Negative 2x is our b. And then our c is what? Negative 1. And according to the quadratic formula, the solutions to this are u is equal to, what was the quadratic formula? Negative b, so that would be what? For us, 2x plus or minus the square root of negative 2x squared. So b squared, what's negative 2x squared? 4x squared minus 4 times a times c. 4 times a times c, so plus 4, all over 2 times a, which is 2. Yes? Let's take a vote. How many of you are with me still here? All right. I'm going to clean this up a little bit before I substitute back. Both of these terms here have 4 in them, right? So I can factor 4 out and then separate it, and the square root of 4 would be what? 2 on the outside, and then this 2, and this 2 would all cancel out, so you'd just be left with what? X plus or minus square root of x squared plus 1. Damn, we're getting close, aren't we? We're getting close. Look, remember what we were trying to get to, right? X plus square root of x squared plus 1, right here. Yes? Okay, but this is what u is. What was u? E to the y. So next page, e to the y, I'm substituting back, must be equal to x plus or minus the square root of x squared plus 1. And now to get y to drop out of this, which is what we were trying to do, right? Get y. Take the natural log on both sides. So the natural log of e to the y will be equal to the natural log of x plus or minus the square root of x squared plus 1. And then that means y must equal natural log of x plus square root of x squared plus 1. And it's only the plus, not the minus, because I don't know why. No, why is it? Can't take the log of a negative number, but why? How can you guarantee me that if this is a minus, this will be negative? Okay, yeah, so let's look at this. X minus the square root of x squared plus 1. Does everybody agree that this right here, right, that right there, is bigger than the square root of x squared. Yes, that's bigger than the square root of x squared? And the square root of x squared is basically x, isn't it? So wouldn't this mean that this thing in the, what is that, yellow, sorry, in the yellow is bigger than x? So if I take x and subtract something bigger than x, it's going to be negative. So, and I can't take the natural log of a negative number. So I'm going to throw out the negative. So this is it. That's pretty neat. So let's vote real quick. How many of you had ever seen anything like that as far as using quadratic formula to solve something? Yes or no? Okay, good. The quadratic formula can be used to solve equations when you have two variables in them. You can still use it as long as one of the variables is quadratic, that you have that form. Okay. Next. Now, you could go and do these also, all right? You could go and do the same exact process. I actually haven't done this one, so I'm not sure how clean that would be. Now, the derivative. How about we show that we're talking about derivatives now, right? Here are the functions. Here are the three inverse hyperbolic functions. Here's showing why one of them was that. And now we're looking at derivatives already. So how would I show that the derivative of cosine hyperbolic inverse of x is this? Well, let's just write it down. If y is equal to cosine hyperbolic inverse of x, I want to show that its derivative is 1 over the square root of x squared minus 1, or yeah, x squared minus 1. All you have to do is take the definition of the hyperbolic inverse first, cosine, which is this. That's the definition of hyperbolic cosine inverse, yes? That's what I said the definition of it was. Now, take its derivative. So the derivative of this would be the derivative of the natural log of something. What's the derivative of natural log of something? 1 over that something? Then chain rule, what's the derivative of what's in there? 1 plus, yeah, again, so this is the derivative of x is here. Derivative of the square root of x squared minus 1 is 1 over 2 root x squared minus 1 times 2x. So look, I am assuming that you can do the derivative of this. It may not look exactly like this, the way you learned it. Maybe you switch it to a 1/2 power first. However you do it, either way, you should be able to get this derivative. And then we should be able to clean this up. So I see these twos cancel. And so we have 1 over x plus root x squared minus 1 times 1 plus 1 over root x squared minus 1. X up there, yes, thank you. Any ideas here on these two? Okay. I'm just going to write it the way it would become after I get a common denominator there. So all I'm doing is turning this 1 into a root x squared minus 1 over root x squared minus 1, putting them together and giving me this. And now what? Multiply them together? I could do that. Something a little easier though. Cancel. This and this are the same factors, aren't they? We're there, aren't we? That's what we were trying to show. Any questions? May I proceed? Okay. The rest of the derivatives for the inverse hyperbolic trig functions can be found in the book. All right. And then I had the one example of a catenary, so this was I tried to motivate this section by showing you the value of having a hyperbolic trig function. Here it is. You can adjust, of course, depending on how you adjust the coefficient here and this number here, you can adjust the catenary to, the spacing of the poles, so to speak. Okay, that should be the homework for that section. All right. 4-7. We move on. So we had talked in the very beginning of this class about how the first test is going to be a lot of this antiderivative stuff. Everything we covered so far is kind of a prelude to that. We haven't done any antiderivatives yet. Everything's been differentiation, so Cal 1 stuff. A lot of Cal 1 classes do introduce you to the antiderivative. So again, you may, for the rest of today and probably part of next class, you may still be familiar, but I'm thinking by maybe the end of next class or the week after, if you haven't seen Calculus 2, then it'll be more new information. And it's going to, once we get into the new stuff, it's going to come really fast. All right? So be ready. All right, so the idea of the antiderivative, all right? A function capital F is called the antiderivative of little f on an interval I if the derivative of capital f of x is equal to the little f of x for all the x in that interval. All right, we'll get to pictures here in a second. If capital F is an antiderivative of little f, then capital F plus c is the most general antiderivative of little f, where here c is any constant. So here's a picture of what's happening. First of all, little f of x is 2x. Then capital F of x is x squared plus a constant. So let's just check to see that capital F is an antiderivative. To be an antiderivative means that when I take the derivative of this, I should get this. And the derivative of x squared is 2x. What's the derivative of a constant? 0. So no matter what number I were to ever add to the outside of that, 10, -5, doesn't matter. If I take the derivative of this, I should get this. Okay. So what we want to look at here is try and get an idea visually of what's happening. Right? Here's we'll start with the 2x. Okay, that's little f. It's a line, right? 2x. Its antiderivative is x squared plus any number. So look at this is x squared plus 1 right here. Here's x squared plus 10. Here's x squared minus 10. So there's 3 more, right? There's 3 of the antiderivatives. But since it was plus c, how many are there? Infinitely many. So I could have all of those, right? All those. I mean, every single one of these parabolas is x squared plus c, and they all have something in common. So what I want you to see that may not be as obvious right now is that if I were to try and zoom in on this so you can see this, all right? Oh, there it is. Oh, I don't need to zoom in. I already did this. It's just hard to see it. Okay, let me get take some of those out. Come on, come back here. Can y'all see these little things right here? These little lines? What are those? Tangent lines, right? It's the derivative, right? All of these curves that come from this same family, if you take the derivative at that point, at that specific x value, look at all of them. They're all the same, right? And this slope of the tangent line here corresponds exactly to the value of this red function. So that's why the red function has a family of functions where it comes from. The derivative of that family takes you back to that red line. So let me try and get an actual value so you can plug one in here. Uh-oh. There it goes. So what I did is I plugged in 1. So if you plug 1 into this function, what do you get? 2. Okay, if we go to the family of functions here, we go out to the x value of 1, and we go up to that tangent line right there, what's its slope? 2. It's 2, right? Because I'm plugging 1 in. I'm going to 1, that's the value. So do you see the connection is that every family has the same slope at that point. If I change the value to 2, what's the slope of the tangent line going to be? 4. So if you come out here, go to 2, on every one of these curves, the family of curves, the slope is going to be 4. Hope that makes sense. Here's another one. Here, the little f is 3x squared plus 10x plus 6. The general antiderivative is x cubed plus 5x squared plus 6x plus a constant. You can check. If you take the derivative of that right there, right, you get 3x squared plus 10x plus 6, and that's this. So which is which here? The red one is little f. The blue one is part of the family of antiderivatives, right? I could throw in a couple of more, right? Any of those would be in the family. And again, do you see the property that they all share the same slope, same tangent line there? I can move this value around, doesn't matter where it is. That entire family shares the same derivative. Now there are some common antiderivatives that everyone needs to know, all right? And they're on page 249 in your book. They're also on your cheat sheet. And they are the antiderivatives of things that you should already know, all right? Like, we'll run through these pretty quick. If I tell you little f is cosine x, then what's capital F of x? Sine x plus a constant. So what we're doing is we're saying this. When we're looking at this, we're saying, look at what's cosine of x is the derivative of something. What is it the derivative of? It's the derivative of sine. What we are not saying is what's the derivative of cosine. The derivative of cosine is negative sine. So we're going backwards, right? So what would be another common one I should know? Sine x? So the derivative of what gives me sine? Negative cosine, right? Plus c. So you're always going to add a c. Because this represents the entire family, right? We call this later on the constant of integration, but right now it's just our constant. What else? Say what? Okay, that's one you know. What's the antiderivative of secant squared? Tangent, right? Because you knew that the derivative of tangent was secant squared. So everyone needs to know now that the antiderivative of secant squared is tangent. So let's see, we could almost work this backwards. Derivative of the sine was cosine. Derivative of cosine was negative sine, so we changed it over here. The derivative of tangent was secant squared. So what would be the next one that we would want to have in our memory banks? What's the derivative of secant or cosecant? What was the derivative of secant x? Secant x tangent x, right? That came from taking the derivative of secant. Do you see what I'm doing? I'm just kind of like reverse engineering all the stuff from Cal 1. These are the things we know the antiderivatives of because we know the derivatives of those. Here's another one. I'm going to stop with the trig stuff. 1 over x. That was an important one. Natural log x. So the natural log, we usually put absolute value of x because you can't plug negative numbers. We don't want to evaluate a natural log in negatives. So the antiderivative of 1 over x would be natural log of the absolute value of x plus c. What else is on here? Okay. Some things that aren't so natural necessarily because we just learned them. This one's going to come up all the time in here. Arctangent. Arctangent, right? That was the derivative. You just learned this last class. This was the derivative of arctangent of x, wasn't it? So we need to be able to recognize from here on out that if we ever have like 1 over 1 plus x squared or 1 over x squared plus 1, either one, that backwards to get the antiderivative, we need to remember it's the arctangent, right? Some other ones that we just learned. Arcsine. And so on and so forth. Pretty much at this point, all the common things that we saw in Calculus 1, the things that we've introduced now, we should realize that, look, we can always go backwards from, from their derivative backwards to their antiderivative. All right, which leads us to the more general, or trying to come up with a general formula for powers of x. What if I have like x squared? What would the antiderivative, general antiderivative of this be? We know it's x cubed, right? Because the derivative of x cubed, the power would come down to give us x squared. But because the 3 would come out and we don't have a 3 here, we would have to what? Divide by 3 or scale it by 1/3. Yes? So what I'm going to do is I'm going to put a 1/3 there and then always throw my c. How about another one? X to the 10th. Same principle, right? We're going to have to do the x to the 10th, but we don't want that, oh, sorry, not 10th, 11th, but we don't want that 11 to actually come out in front, so we need to scale by it. 1/11th, right? So it's almost like every time we go backwards, we're adding 1 to the power, yes? And then we're scaling by 1 over that power. So what we can do is we can come up with a formula for this that would look like this. X to the n should go backwards to become, what's going to happen to the power? N plus 1, and then I should scale through by 1 over n plus 1, and then add a constant. And this right here is the power rule for antiderivatives. Quick little poll. We good or not here? Does anybody see an issue we might run into here where this formula would break down? If n is -1, right? Because if n is -1, what's -1 plus 1? 0, and you can't divide by 0. But if n is -1, isn't it this one right here? That's x to the negative 1, isn't it? So in the event that that n is negative 1, you already know the answer was natural log x. So we need to add a little condition onto this formula, all right? This only works, I'm going to throw it here on this side, if n is what? Not equal to negative 1. If n is negative 1, the antiderivative is just natural log of x plus your constant. So make sure you add that little condition on there. And this rule works for all powers of x, even rational exponents. So if we have something like this, the antiderivative of this is not natural log of the absolute value of x. We first have to rewrite this as x to a power. So let's rewrite it as x to a power. This is the same as x to what power? Negative 1/2. Now, can we use this formula if the n here is negative 1/2? Yes, as long as it's not negative 1. So to go backwards here, it's going to be 1 over the n that we have, which for us is negative 1/2, and then we're going to add to that 1, and then x to the negative 1/2 plus 1, and then plus our constant. Does everyone see that this is just applying the formula to this? No? All right, and then the more you do this, hopefully you're pretty comfortable with fractions to begin with, but the more you do this, the more comfortable you get, and eventually you start to do it almost automatically. What's negative 1/2 plus 1 is 1/2. What's 1 over 1/2? 2, so you just reciprocate it, right? So this just becomes 2 x to the 1/2, which is the same as 2, I forgot my plus c, which is the same as what? 2 root x plus c. You could leave it like this, okay? This would not be wrong. But if you're checking answers in the back of the book and you see that, you don't want to be like, man, I don't know what happened. All right. Let's do some examples here. I'm working off my notes now. I'm doing example 1. I'm going to give you some functions, and we're going to work and try and get their antiderivatives. Now here, I'll let you write that down. We are trying to go backwards, right? This is the derivative of something. What is it the derivative of? Well, let's first notice that we have 3 terms, right? Okay, do you remember with derivatives? Like if you were asked to take the derivative of something like this, that's not what we're doing, but if I said take the derivative of this, you could do the derivative of each of those 3 green pieces, right? Because that's the way derivatives worked. The derivative of a sum was the sum of the derivatives. So you could very nicely separate them one by one. Antiderivatives work the same way. If you have sums or differences, you can find the antiderivative of each one separately and then combine those answers into one final answer. Now, in Cal 1, when we took derivatives of products, what happened? You had product rule, right? When we did derivatives of quotients, we had quotient rule. When we did derivatives of compositions, we had chain rule. So imagine trying to undo a product rule, or undo a quotient rule, or undo a chain rule. That's what the heart of your next test is about, is undoing things that are very complicated. Right now, this is very basic. We have addition, subtraction. Further, each one of these 3 terms can be represented as x to a power. Every one of them can be rewritten as x to a power. If we can do that, we can use the power rule, right? So let's try and rewrite all of these as x to a power before I take an antiderivative. The first one, 2/3 x to the third, there's nothing to do there. That already has a power on x. I'm happy. Plus 4 now, square root of x is x to what power? 1/2. Minus x to the 3/2, right? We're going, I should probably circle the whole thing. That's x to the first power times x to the 1/2 power. That's what that is, right? So you add the exponents. 1 plus 1/2 is 3/2. So we have x to the 3/2 there. Okay, real quick, are we good or not? So now let's find capital F. Well, again, let me go back to the analogy in Cal 1. In Cal 1, what was the derivative of sine x? Cosine x. In Cal 1, what was the derivative of 4 times sine x? 4 cosine x, right? The 4 just came along for the ride, didn't it? When a number was attached to a function and you took the derivative, the number just came with you, right? Same thing with antiderivative. If you have a number in front of the power of x, that number is going to come with you, backwards. So what I'm going to do is I'm going to ignore the 2/3, and I'm going to bring it into my answer and focus all of my attention on just trying to figure out what the antiderivative of x to the third is. Now, using that formula. So it should be 1 over 3 plus 1 is 4, x to the 4th power. Then I'll say plus. Then that 4 right here is going to come along. And then times this part right here, using power rule on that. So 1 over, I'll say 1/2 plus 1, just to go a little slower. X to the 1/2 plus 1, which will be 3/2. And then minus, last part, 1 over 3/2 plus 1, x to the 3/2 plus 1, all of this plus c, right? It's just cleanup time, all right? Let's clean this up. What's this? 1/6, x to the 4th. All right. This is 1 over 3/2, which is the same as 2/3. So 8/3. X to the what? 3/2. And then over here, this was 3/2 plus 1, which is 5/2. 1 over 5/2 is 2/5. So we'll get minus 2/5 x to the 5/2 plus a constant. All right, quick vote if you're good or not. You may have to work on your fraction stuff, okay? It's, you know, if this is your first exposure to antiderivatives, you'll realize after doing a bunch that these fraction things just start to hopefully get going pretty quick. Yep, that's all you have to look at it as. It is the reciprocal. Now, could you do more to this to make it look different, maybe match the back of the book? Yeah, probably. We should all at least be aware of something like this is the same as x cubed square root. That's what that means, which you could look at as being like break it up where you can peel off a pair like that, and then you could rewrite that as x root x. So the back of the book might have something like 1/6 x to the 4th plus 8/3 x root x. And then that last one, x to the 5/2, would actually be what? X squared root x, if you did that one the same way. So just be aware of that. I have no problems at all with you just leaving this with rational exponents. Okay, let's look at another one. Oh, wow, we're almost out of time. I had a quiz for you today, but I didn't realize I talked so much. Well, you actually had gotten kind of lucky because number 2, someone asked me about. It was pretty much just like the homework in number 3 was like one I did in class. Let's do this. I don't want to waste this paper, and it was a quiz grade. I'm just going to say you take it home and bring it back, okay? It may not carry the weight of a full quiz, all right, but it'll be something for you, all right? Just bring them to class on Wednesday. While that's going around, let me set up the next problem. They'll come around. Still don't have enough? I printed 26 because I had 26 students in here initially. So I don't know. I guess my enrollment went up a little bit. If you don't have one, just how about you email me or follow me to my office after class. If you email me, I'll send you a copy. You can. It's just that risk if it looks different than other things, it might just get like, go off into an abyss somewhere. Okay, in the last 3 minutes, let's take a look at this. If you were back in Cal 1 and you were asked to take the derivative, right? You might be thinking quotient rule, maybe, right? But because you have a single term in the denominator, what can you do? Split it up, right? These are all powers of x. Everything here is a power of x. Well, what about 4? That's x to the 0 next to that, right? So that is a power of x. These are all powers of x over a single factor in the denominator. So before I do any antiderivatives here, I'm going to split this up. And because of time, I think I will jump a little bit here. So I have not taken an antiderivative, right? All I've done is algebra at this point, splitting it into 4 different terms. Now we got really lucky here, okay? Because look at this problem. If I had put +1 right here, right? If I had put +1 here, would this have turned out to be something so nice? No. Okay, so we got really, really lucky. So you want to be looking for things like that. If you have one term in the bottom, split it up. Now you have to use exponent properties to rewrite these all as powers of x. So let's do that. I've got maybe 30 seconds. What's this first one? 2x to the 2/3. How'd you get 2/3? You took the power up top, which was 1. You subtracted the power on the bottom, 1/3. 1 minus 1/3 is 2/3. And then you keep doing this for the rest of these. Plus, what's 1/2 minus 1/3? 1/6. What about the next one? You bring the x up. Very important. If you're going to apply the power rule, the 4 stays. This x to a power has to come up. So it becomes an x to the negative 1/3. And then this last one, x to the 8/3. And now you go find your capital F. And to do that, you use, these are your different powers up here. So you got to use the formula, 1 over n plus 1, x to the n plus 1. We good? Okay. If you want to get started, there's the homework for the next section. I know some of you have seen this already, so if you want to start getting a little ahead, I'll wrap up 4-7 on Wednesday very quickly at the beginning of class, and then we will start 5.5, that's substitution, then we get into integration by parts, and then we start to get into the heavy antiderivative stuff. Please leave your clickers, don't take them home with you. Yeah, just when I finish that section, then that night for homework before we meet the next class is when it would be due. 3-5 is done, so 3-6 and you could start this. There's a little bit more we could do on this. That's right. But if you're comfortable with this, then try and do as much as you can.